Yeah, so thank you very much for the introduction. My name is Jonas. I'm doing this talk jointly with Philipp, and we are going to present you the I2 visualization framework for real-time visualization of streaming data, which is built basically on top of Apache Flink and Apache Zeppelin. So let me give you a short summary why it's worth it to postpone checking your mails for that talk. So what we do is we connect Flink and Zeppelin to visualize data streams in real time. But what we also do is we make the front-end settings, so what you actually select in the visualization, available to the Flink job. And depending on what you select, we manage to adapt the running Flink job to only process and stream the data which you're actually going to need for your visualizations. Thereby, we reduce the amount of process and transferred data while we still provide loss-free plots. So in our example, this means that we roughly process 12,000 events per second without crashing the front end, which is executed in the browser. Of course, this could also scale like to larger clusters and so on. And using Apache Zeppelin, which is like similar to IPython notebooks, we also enable the visualization-driven development of Flink jobs. And this point actually brings me to what I2 actually stands for. So why we chose that 2 is we wanted to highlight the 2 types of interactivity which we provide here. And the first way of interacting with I2 is through the code changes. So we wanted to have this iterative exploration of data and development of a Flink job on streaming data while you can actually see the live data. So we do that, and we allow you to have this visualization basically next to your code, and then to easily redeploy changes to the UI component, but also redeploy changes to the Flink job. And the other way of interactivity we have is the interactivity in the visualization UI. So saying you select a certain filter predicate, you zoom into a map, or we will show you some examples where we select players we want to monitor in a football game. And then we also wanted to have that interactivity so that we adapt the running Flink job without a need to restart the job, so to adapt with very low latency here. So let me give you a short overview about how our architecture for that looks like before we then step into our use case and the demonstration. So in general, the architecture is we have here on the left our Apache Flink cluster, and on the other side we have Apache Zeppelin. Apache Zeppelin basically consists of our development environment, from which we also deploy our data analysis or stream analysis applications in a one-click fashion. And then we have a visualization front end, which basically has a feedback stream where we send the properties or the setting changes you make at the front end. And then we use the co-flat map operation to merge the information about the properties with the actual data stream, and depending on what we have there, we can apply a data reduction, basically reducing the amount of data we have on this edge so that the UI stays responsive and you don't have to send too much data to your users, which actually watch the dashboard. So, of course, there are manifold use cases for that, but what we show you is a use case based on data from a football match, which was recorded and provided in 2013. So you can see here on the right how that basically looked like. There was the football. In the football, there's a sensor in the middle, and the same sensors were also placed at the shoes of the football players and at the hands of the goalkeepers. And then all the data was recorded with up to 2000 Hertz frequency, which results in roughly 12K data points per second. So now I hand over to Philipp, and he will show you a bit how that looks like in the live visualization.
So, first of all, I want to show you our dashboard. So this dashboard combines all our UI components, and yeah, it's really interactive. So on the right lower side, we see all the football players moving on the football field, and the user can maybe observe different patterns, like what is the defense doing and so on. And on the top, we can then select, for example, players to focus more on them, and we see they get highlighted on the football field. And on the lower left, we have a line chart where we can focus on different properties of the sensor data we get. So we can, for example, select the velocity or other properties, or we can even select the time frame which is visualized in the line chart. And on the top we see some statistics like how many raw data items we process in our Flink job, and how many items or data items are transferred to our UI. So we see that we reduce the amount of data really heavily, and when I now, for example, select an other time frame here, we see that the number of data items which are transferred to the line chart are reduced, and that is also the main motivation for our system, that we want to reduce the data items in the backend at most as possible, so that we don't have to process them in the front end. And I will now dive more deep into our Zeppelin notebook, which combines all the UI components and the Flink job. And as you maybe know, with Apache Zeppelin, I can create Flink jobs directly in this nice web interface. For example, here I combine the different streams to the data sinks and so on. And we extended Zeppelin a bit so that we can also create this interactive UI components in the UI. And I will have to scroll up a bit. For example, here we create the line chart, and as you can see, it's just some JavaScript which is executed in the web front end, and we have created an Java interface which can be extended, and this interface allows us to communicate between the front end in JavaScript and the back end Flink job. So for the back end Flink job, this is just a data sink or a data source. So it can receive data from Flink, or it can even push data to Flink. And we are using this component then to, for example, send properties from the visualization back to the Flink job to react there on these properties, or to receive data as a sink. And I will now hand over again to Jonas, and he will dive more deep into the architecture and
So thank you, Philipp. So now what you basically saw in the demonstration was mostly that visualization front end, and the interesting part about that is that it's completely independent, more or less, from the actual running Flink jobs. So you can have very fast development cycles or redeploy cycles on that front end. And continuing a bit on what Philipp explained to you just before is, whenever you select a player here, click on that button, it's not only that something in the visualization changes, it's also that we have that feedback stream. So any action you make in the UI, we stream basically back to Flink and can react on that. In our case, it's very simple things like we change a filter predicate, or we change the output from having a different windowing granularity. However, if you think a bit further on that, you can of course also send, for example, a complete UDF and exchange the complete operator logic of an operator which is running. So there's not much of limitation here. So to stress this a bit, let me show you how you can use that co-flat map operation as one example for having an adaptive Flink operator. So what we do here in this example is we basically just have an adaptive filter. So what this co-flat map operation does in Flink is it has two different input streams and one output stream, and each each input stream is passed to its own map function, but both map functions share a common state. So what we do here is we have our control messages. These control messages go into a map job which basically stores a threshold, and depending on that threshold, we apply a filter here in the bottom. So for example, we can say we want to have all values smaller than 15, then we send a 15 here as a control message, and this filter will adapt. Thinking about that, in this map function here, you could also have your complete user-defined function, a different aggregation logic, more complex filter predicates, anything like that. So taking this architecture of merging two streams gives you a high flexibility to adapt your Flink jobs at runtime and to react on certain side effects which you have outside of your Flink job without a need to always restart or redeploy the job. So this brings me to the aspect of data reduction. You may remember on the upper left we had this line chart, and there's something very special about that line chart. Because if we are talking about big data, in our case 12,000 events per second, it's completely ridiculous to stream 12,000 events per second to that line chart, because nobody will be able to see 12,000 events per second in the plot. Actually, there's a proof on that it's sufficient to have 4 data points per pixel column. So even though we have maybe 6,000 events per pixel column, if we only have basically the first value for a pixel column, the last value for a pixel column, and the max and the minimum value for a pixel column, there we can prove, and this was basically presented in that VLDB paper here, that there will be a loss-free visualization. So the plot will look exactly the same as if you would stream the complete data. This original paper made that only available for an SQL rewrite. What we did here is we extended this to a streaming fashion. So what we basically do is we figure out how long is our depicted history in the plot. Then we figure out how many pixel columns do we have per time. So let's say you have 5 pixels per second, and then we see to which time frame corresponds one pixel column. So what we can do then is we can do a tumbling window with the length of a pixel column and get exactly those 4 aggregate values, the minimum, the maximum, the first and the last I was just talking about before. And having that said, we come to the situation which Philipp showed you when he changed the windowing granularity from 5 minutes to 30 seconds and so on, that you actually, however you select the depicted history, the I2 framework will make sure for that line chart that it only sends the required data. More importantly, what we can also do here is we can make sure that we have a fault-tolerant application. So we can basically put the regular watermarking in our data source, then we have the tumbling window with 1 pixel range, and we have this M4 aggregation for each window. And then we can do another data compression for the y-axis. But more importantly is that fault tolerance aspect, because if you receive late data, it's very improbable, if you think about it, that this data will change the visualization. So we can then first check, does this late tuple change one of our aggregates, so max, min, first, last, or doesn't it? And if it changed one of the aggregates, we can again check, is this aggregate still displayed in this depicted history, or is it not visualized either way? So we only have to send the update notification to the front end if a late data point actually changes our plot. Otherwise, we can prevent additional computation load at the front end here. So, to wrap this up, let me briefly show you how the dashboard basically performs with using I2, so what Philipp just showed you, and without. And what you can see here is without I2, we start the data transfer in the beginning, then the UI is able to keep up with the processing for a certain time, so we stay close to the 60 frames per second which the screen can provide us. However, after a while, we get a lot of scripting overhead, which is because the processing in the browser cannot keep up with the 12K data points, basically. And this drawing and painting takes a lot of load, so we cannot keep up with the frame rate, and we get a UI crash. And this pressure is basically avoided when we have I2, because we can put all that load to the Flink cluster, where we are able to scale, while the user who uses the front end will always receive like a constant bandwidth stream, which is visualized live, and then you can see that we always stay like up also on a long duration with the 30 frames per, with the 60 frames per second, and we continuously have here mostly the painting effort, but not so much scripting effort, because there's basically not so huge complexity in the front end. So with that, I think we have about 5 minutes left for any questions, discussions, and so on. So I would like to start a bit in a Q&A session. But before we go to that, I want to briefly summarize what we actually did. So we have the live visualization with Flink and Zeppelin. We adapt jobs to change settings at runtime. That's an important feature. We reduce the data transfer and the processing effort without a quality loss in the application. And we wanted to support the easier development of live visualizations. Since we are from a university, all that is open source, so please feel free to check that out, to maybe give us comments how we can improve on what we have there, or how you use that, or any other ideas are warmly welcome. Yeah, and we have on the right like all the projects who were supporting that, especially the Streamline and the Proteus project and the Berlin Big Data Center. So also thanks to them. Okay, any questions? There's one in the back.
Did I understand it correctly that you are modifying the time, or the amount of time that the time window size of a window operator at runtime?
Well, in our setting at the moment, we have basically several window operators running in parallel, and we switch which output we use. Okay. But there's basically nothing what would prevent you to implement an adaptive window operator with that CoMap syntax or CoMap-like way. It's just that this is at the moment not natively present in Flink, which is why we use the switch between several outputs or several window operators. But I think it shouldn't be too hard to adapt the Flink window operator such that the tumbling window changes its length, because that's just like a single variable, which is the state in the tumbling window. So it's not so hard to adapt that.
Well, except probably like windows that are already in progress.
That what?
Windows that are already in progress.
Yeah, if the window is already in progress, you can basically only say that you want to end it. Technically, you can. At least if it's pre-aggregated. If you keep the window in a bag or in the map, and you have the individual tuples, you can of course change the granularity at any time technically. Further questions? Yeah.
Thank you for the talk. I have a question. So if I want to build my own dashboard with my own data, what are the requirements? Do I need to be a programmer, or is it necessary to know everything about Flink and the APIs?
So basically what we provide you here is we have this interface which Philipp briefly showed, where, yeah, maybe you can step back to that, which basically integrates in Flink as a sink. So you can send the data you need by just implementing this interface as a sink, and this will then connect to the front end. For the visualizations, you are basically free to either take existing JavaScript visualizations. So we, for example, took a lot from D3.js, which is kind of widely used. And you can, of course, configure your sink there such that it already sends out the JSON data or whatever D3.js components would expect. So this does not need a lot of work to adapt. For the soccer field map, for example, we just completely implemented that from scratch, so we can do that as well, of course. But you need to be a programmer to the extent that you must implement the sync on yourself, and we do not have pre-made Flink job components going beyond that. So we are not dealing with the data analytics, more with the merging the control streams and the actual data streams.
Thank you.
Yeah. I think the session chair will interrupt if we run out of time. Otherwise, we continue. So just tell us when we should stop.
Thank you for your talk. It was really interesting. I have one question related to, you said theoretically we could also send new, I don't know, UDFs or chars to my job to adapt. Like, do you see that this would currently work already, and if so, how do you do that?
I mean, the basic thing, what you could do is you can basically send a class file which nests, for example, a filter function or a UDF implementation as binary, and then you can store that to the state of a COMAP operator or any other operator, and then execute it whenever data arrives. So that would already work.
Oh, okay. Thank you.
But I mean, that it would be, I mean, if you bring that into production at a larger scale, you may end up at a point where you want to optimize this a bit further and have a more native implementation of that, that's for sure. Okay, so thank you very much. If there are further questions, we are around today and tomorrow, so feel free to contact us at any time.
Thank you.